Hello, everyone. I'm going to go over this Markov chain example problem. We ran out of time in class to go to the end here. So I'm going to try to just explain this problem and the logic behind it step by step. Okay, so let's get started. There are two urns, A and B in a casino game. Initially, A contains two red marbles and B contains three blue marbles. So let me draw this out over here. Okay, let's say A and B or one and two, earn one, earn two, or earn A and earn B. The A contains two red ones, okay, and then B contains, let's say, three. Okay. At each player iteration here, marbles are shuffled repeatedly at discrete time steps according to the following rule. We pick a random one marble from each urn and swap them. So basically, we pick one randomly, and we just swap. Okay, and we do this repeatedly. Can we model this as a Markov chain? Is this an ergodic chain, absorbing chain? What will happen to this game after many repeated plays? Let's try to answer all of that. Really, if we can show that we can set this up as a Markov chain, and if we can, find the limiting probability, then we know this is an ergodic chain. Or another way to think about it is if it's ergodic, we know we have a limiting probability. That's what happens after many repeated plays. If it's an absorbing chain, that means we're going to have probably some set of recurrent and transient states. And then after repeated plays, we're going to end up in one of those recurrent states, right? So whichever path we go, we have to set up the Markov chain first, okay? So then the question is like, how do you set this up as a Markov chain? It's much easier in this problem if you were to just focus on one of these urns and not both. So if I were to isolate urn A on the left here, if I know what's going on in urn A, I know what's going on in urn B. For example, if there is one red and one blue in urn A, that means I have one red and two blue in urn B. If I have two blues in the urn A, then I have two red and one blue in urn B, right? So I know what's going on in both of these urns if I just focus on urn A. Okay, so using that logic, then I only need three states. Okay, so state 0, 1, and 2. And then interpretation. 0 means no red in A. 1 means one red in B. And then 2 means two red in B. Okay. And if I have those three states, then I can describe this problem in entirety. Okay. So using those three states, okay, let me set up the transition matrix here. Okay. So let me set up the transition matrix. Here we go. 1, 2. Okay, so let me see if I can draw this out step by step. So you will kind of see what we're going. So state 0, I'm going to represent it as no red in the first turn, right? So I have basically two blues on the left, and then I have one blue, and then two red on the right. Okay, so again, we're only focusing on the urn on the left. Okay, so if I set up my transition matrix 0, 1, and 2 like this, can I transition from 0 to 0, 0 to 1, 0 to 2? Okay, so 0, 1, let's put it like that. Okay, so can I start at this picture and end up in this current picture? Okay, the only way that could happen is if I were to choose one of these two, okay, which is 100%, right? And I were to pick this blue one here, right? And if I make that swap, if I were to make that swap, then I'm going to be in the same picture the next time around, right? So that probability is 1 times 1/3, which is 1/3. So that probability is 1/3. Okay. Okay, let me delete that over here. Let me look at state 1. Okay, so this is state 0. Let me draw a state 1 here. 1 means one red, and the rest are blues, right? So we have one blue and two blue, and this is state 1. Okay, so can I transition from state 0 to state 1? Can this happen, right? The only way for that to happen is if I were to pick one of those two blues, right? Okay, and then pick any one of these two reds, right? Okay, and then swap. Okay, so that probability is going to be 1 times 2/3, right? So then the value is 2/3. This value is 2/3. I can't go from no red on the left to two reds. that probability is 0. Okay, so that takes care of the first row. Okay, let's look at the row. Let's look at state 1. Okay, so I'll keep these picture up here as a reference here, or I'm gonna keep drawing on top of this. Okay, so the second pick, the state 2. Before I go to state 2, let's start with state 1. Okay, if I'm currently in state 1, right? Can I go back this way to state 0? Can that happen? Okay. You can, right? If you were to pick this red and then pick one of these two blues and swap, then you'll get there, right? Okay, so that probability is 1/2 times 2/3, okay, which is 1/3, right? This value is again 1/3. Okay. Can I stay in state 1? Okay. Can I stay in state 1? Can I just stay in this same picture? The answer is yes, right? You can. And let me draw out those cases. Okay. First case is if I were to pick this blue right here and then pick one of these two blues and swap, I'm in the same picture, right? So 1/2 times 2/3. There's another case, right? If I were to pick one of these reds, the red on the left, the red on the right, and then swap, then I'm in the same picture again, right? So 1/2 times 1/3. That's gonna be, I'll keep it in 2/6 plus 1/6, 3/6, 1/2. This will be 1/2. Okay. All right. So yeah, there's a way to stay in state 1. Okay. So let me draw this. Let me erase these right here. Okay. And then now let me draw state 2. It looks like this. Two reds, right? So let me 3 blues here, and then let me put the 2 reds on the left here. Okay. Can I go from this picture to this picture? Can that transition happen? The answer is yes, right? If I were to pick this blue one and this red one and swap, okay, the probability is 1/2 times 1/3, 1/6. Okay, so 1/6. Another way of getting this is just 1 minus 1/3 minus 1/2. But visually you can tell why this is 1/6. Okay, so we have the state transitions from state 1 established. Okay, now let's look at state 2. Okay, so I think the state, this is probably the easiest one to look at. Okay, so if I were to look at state 2, can I stay in state 2? Can I stay in the same picture after a transition? Okay, I don't think you can, right? You're gonna have to transition into state 1, right? It has to, right? Because whichever you pick, anyone you pick, you're gonna end up with 1 red and 1 blue on the left side. Okay, so that probably is gonna be 1, and the rest will be 0. You can't go from 2 reds to no reds. You also can't stay with 2 reds, right? So that's my transition matrix. Okay, now let's set up the limiting problem. So I know this is a this is my Markov chain. I already know, I can actually see that this is already a ergodic chain, right? Every state communicate to one class, all recurrent. So this is just one class, right? Everything communicates. So I know these are 3 states, they're all recurrent, and they all come back to each other infinitely many times. Therefore, this is an ergodic chain. Okay, so that means I have a limiting probability. Okay, so how do I get the limiting probability then? Pi 0, you just read down the column, right? Pi 0 equals to 1/3 pi 0 plus 1/3 pi 1. I'm just reading down the columns, right? And then pi 1 equals to 2/3 pi 0 plus 1/2 pi 1 plus pi 2. And then pi 2 equals to 1/6 pi 1. And I have my final equation, pi 0 plus pi 1 plus pi 2 equals 1. Okay, so how do I solve this question easily? I think you have to strategize here, or you're going to get into the circular, argument. You might get stuck forever. I like to use this last equation here to solve. Okay, so let me solve for pi 1 first. Okay, I'm going to solve for pi 1. Okay, the reason I want to do that is because I already have this equation here, which already does a substitution for me. So I'm going to take advantage of that. Okay, so I'm going to take this and substitute it in there for pi 2. I have to get rid of pi 0 now, right? And unfortunately for me, I have this equation over here. Okay, pi 0 equals to 1/3 pi 0 plus 1/3 pi 1, if I rewrite this as 2/3 pi 0 equals 1/3 pi 1, which means that pi 0 is 1/2 pi 1. Okay, so I'm going to substitute this term over here. So what we end up getting is 1/2 pi 1 plus pi 1 plus, let's see what that was, 1/6 pi 1 equals to 1, right? So then 3, 6, 9, 10 over 6 pi 1 equals to 1. So pi 1 equals to 3 over 5. Okay. Once I have that, I can substitute back in. Okay. Pi 0 equals to 1/2 of pi 1. So it's 1/2 of 3/5. Okay, which is 3/10. And then pi 2 is 1/6 of pi 1. It's 1/6 of 3/5. So that's 1/10. Okay, so at the end, I'll write this in decimals to just kind of save some space here. Pi 1. There are those three values, right? So what this result tells me is if you keep playing this again and again, 30% of the time I'm going to be in state 0, 60% of the time I'm going to be in state 1, 10% of the time I'll be in state 2. So which means 10% of the time I have 2 red marbles in the first turn, 60% of the time I have 1 red marble in state 1. I'm sorry. 60% of the time I have 1 red marble in the first turn, okay? And 30% of the time I have no red marbles in the first turn. That's what this result tells me, okay? All right, so let me go to the next part here. Banker decides to gamble on the game. He enters the following bets. It's each time step, the bank wins $9 million. If there are 2 red marbles in earn A, but has to pay 1 million otherwise. What will happen to the bank? Okay, so what happens in this situation? Okay, so we need the results from the last part to answer this question. Okay, X is make sure there's no more here. Okay, so I'm gonna let X equal to the banker's winnings. Okay, this is a random variable, right? Okay, and X here is a discrete random variable, right? Okay, so every play, X is basically $9 million or -1 million. So the banker wins 9 million or loses 1 million. Okay. So what I'm really looking for here is the expected value of X. Okay. So then that's the sum of the value of X itself, probability of that happening, right? Okay. So if I write this out, then it's $9 million, probability that X equals to 9 plus -1 times the probability that X get rid of that apprentice there. X equals to -1. Okay. So what's the probability that I'm sorry, not 9. What am I doing here? Okay. I'm sorry. You win $9 million. Okay, I'm sorry. This is not, yeah. It's technically not this, right? It's, let me be more specific here. 9 million times the probability, there's 2 red marbles, right? So 2 red in A, okay, and then plus -1, probably that you either have 0 or 1 red in A, right? If you have that situation, this is characterized situation, right? Okay, so where do I get these probabilities? Okay, these are my pi's, right? The limiting probabilities, right? So it's 9 times, let me get rid of the parentheses there, pi 2 plus -1 times pi 0 plus pi 1, okay? So 9 times, I think this was, let me go back, 0.1, okay. 0.1 plus -1, I think it was 0.2 plus 0.3, I believe, and 0.6, okay. So if you multiply this aloud, you're gonna get 0. So the expected value here is 0, okay. Hopefully this helps you understand regarding matrix, how to set up the chain, how to use these limiting probabilities pi's to answer this question. Okay, hopefully this clarifies some of the maybe some doubts you had on this. Okay, so thanks for watching. Take care. Bye bye.